In this video, we're going to introduce the idea of electric current. Previously, we talked about parallel plates, and when you have a parallel plate that is at one potential and a second parallel plate which is at another potential, that there is a potential difference that exists between these parallel plates. And that potential difference creates an electric field between them. Well, this is a basic battery. Okay? What we have is a source of energy. Remember that potential is energy per charge. So what we have is a source of potential energy. This is a battery. And one of the first types of batteries were these electrochemical cells, which were basically two different types of copper, in this case two different types of metals, sorry, in this case copper and zinc, in an acid bath, in this case sulfuric acid. The acid and the metals interact, there's a chemical reaction, causing the copper to become positively charged and the zinc to become negatively charged. So there you have your parallel plates, your source of potential difference. And what we end up having then are electrons, when we connect up the zinc and the copper, electrons flowing around from the copper to the zinc, and we have a source of electric current. Okay? And that's what current is. Current is symbolized by the letter I, and it's the flow of electric charge. So it's charge divided by time. So if we looked at the units, this would be measured in how many coulombs of charge per second. Okay. And rather than talking in terms of coulombs per second, we say that 1 coulomb per second is equal to 1 amp. Okay, so the units for current are amps, an uppercase A, which 1 amp is equal to 1 coulomb of charge every second. So basically what we're doing is we're counting how many charges pass through here per second. Most modern batteries, in this case we have like a basic D-cell battery here, operate in the same way. We have parallel plates or two metals, in this case a carbon piece of metal through the center, and zinc, which is the outside here going around, which is the other parallel plate or the other metal. So we have a carbon and a zinc, and they're encased in this electrolyte paste. Okay, it's no longer a wet battery. That's why we often call them dry cells. And if you've ever seen a battery that's been left in a device too long, you'll start to see this paste starting to leak out. But it's still an acid, okay? And the chemical reaction still occurs between the two metals. One becomes the positive plate, the other one becomes the negative plate, which is why the pointy end of the battery is positive whenever you plug it into your device. And if we connect the two plates, we create what's called an electric circuit. And we get electrons flowing from the negative to the positive plate, and those electrons can pass through a device, in this case a light bulb, and they give up some of their energy to power the light bulb. So they gain energy when they pass through this potential difference, right? So we have a potential difference, so a source of potential energy. So the electrons leave the battery with energy, and they pass through the light bulb and they give up their energy. And then they travel back to the battery, gain more energy, come back, give energy to the light bulb. Okay. That's a basic electric circuit. So what we have is potential difference, we have current, and then we have a load. And we often call the load resistance, symbolized by a capital R. And resistance is measured in units called ohms, and they have the Greek letter omega, which kind of looks like a horseshoe. and resistance is measured in ohms. And we actually have a law called Ohm's law, which relates these three quantities, that the potential is equal to the current times the resistance. And this is called Ohm's law. V equals I times R. Okay, if we were to draw this circuit in our textbook, we would draw a circuit diagram, and it might look something like this. This one actually has two resistors. So again, we have our potential difference, and the symbol for a battery are two parallel plates, one representing the positive plate, which is always the longer side, the other one the negative plate, which is the shorter side. So here's our potential difference, and then we have our resistors, and resistors have this sort of squiggly looking line, and then we have current flowing around this circuit. Now, electrons and protons are relatively new discoveries. People didn't know about them until the last sort of 100 years or so. But electric circuits, electricity is slightly older than that. So when people like Benjamin Franklin were talking about electricity, they talked about the electric current as the flow of positive charge. So we still keep that notation, even though we know that the protons themselves are not moving, that it's actually electrons going around the circuit counterclockwise. We still draw the current itself. Let me draw the current in a different color. The current itself goes in this direction in our circuit as if it was the motion of positive charge. So here's my electric current. It goes through, around this way, through these resistors, and then back to the battery. Okay. There are some reasons that we'll talk about in electromagnetism about why we keep this notation that current is the motion of positive charges, even though we know it's not exactly true. There are some reasons for it that we'll see later. So the thing to remember is current is always the flow of the direction that positive charges moves. And that's important to remember about our circuits. Okay, in the next video we're going to talk a little bit more about the different types of circuits and how we can use Ohm's law to determine unknown quantities in the circuit. Okay?